up for Audrey.
Thank you. That was a great warm-up, App. I'll just get started. OK, I think Apple really wants you to add machine learning to your apps. And in this talk, I'll show you some of the tools you can use to get started. First, let me establish some credibility. Ray Wenderlich provides tutorials, books, and video courses to teach people to develop iOS apps. I joined the team 4 years ago, after 25 years as a computer science academic. You might have seen my watchOS book chapters, or my video courses, or my tutorials. After Ash's talk, I can say I'm a technology generalist with expertise in translating new knowledge into learning materials. When Apple announced CoreML last year, we published a tutorial about it on the last day of WWDC. Earlier this year, I wrote a tutorial on Keras and another on Watson services. And then this year, Apple announced CreateML, machine learning in Xcode and Swift. So I wrote a tutorial about that, and it appeared the Tuesday after WWDC. Apple started publishing a machine learning journal last year. The November article explained how they built their vision framework model. It was kind of technical and aimed at researchers. At the end of the article are these suggestions for how to get started. You watch the video, you read the documentation, and you do this tutorial. That's my tutorial. Thank you, Apple. So, what is machine learning? Machine learning gives computers the ability to learn without being explicitly programmed. And why would you want to do that? Well, it's easy to program computers to do repetitive things that people have to think about to do, like scientific calculations. But it's very hard to program computers to do things that most people do without conscious thought, like recognize faces or objects or the meaning of sentences. It's hard to write down an algorithm. What's the human brain actually doing? How would you write down rules to recognize your face in a photo? Or explain to a small child the difference between cats and dogs using only photos? These are some of the breakthroughs in deep learning, which is the hottest area in machine learning. Oh, and what's the difference between AI and ML? Actually, machine learning is a subset of artificial intelligence. AI includes a lot of explicit programming, like expert systems. So if you can't write the exact steps for a computer to recognize objects in an image, or the sentiment expressed by some text, maybe you can write a program to produce an algorithm that does the job. You give the program a lot of training data, and you let the program calculate how to transform and combine this data to get as many correct answers as it can. You label each data item with the class you care about, so the program can compare its predicted labels with the true labels and compute its error. The program uses its error to adjust the algorithm's parameters, and it iterates until it reaches a minimum accuracy or a maximum number of iterations. The parameters are the weights the model uses to combine features of your data to predict the correct classes. When your data is in table form, the features are the columns. For a model that predicts house prices, the features include the number of rooms, the floor area, the street name, and the sale price for each house in the data set. But for an image classifier, you just supply labeled images, and you let the model find features in the image data that turn out to be useful for getting correct answers for this data set. So you train a model on a computer because training needs a lot of computing power. To use the model, you give it new inputs, and it calculates outputs, and this is called inference. Inference still requires a lot of computing power, and doing these calculations on iPhones is possible because of Metal. As Eileen said, doing inference on device gives faster response to the user and is good for user privacy because their data doesn't go to a back-end server for processing. Deep learning is about neural networks, which try to model the human brain processes with layers of nodes. Neural networks need a large amount of training data. The explosion in user-generated data is one factor in the recent success of deep learning. Training a network requires a lot of computing power, but the calculations are matrix operations, and GPUs handle these very fast. All of you who bought game-playing devices over the years helped to bring down the cost of faster GPUs, making it possible to train neural networks many layers deep, which is why it's called deep learning. So, is it hard or a lot of work? It depends which level of abstraction you need to work at. Apple provides tools at the task level, like image or text classification. CoreML was announced with a few existing image models. Apple has several frameworks, like vision and speech. CreateML and Turi Create use transfer learning to let you customize existing models with your data and classes. At the task level, as Apple's web page says, you don't have to be a machine learning expert. These cover most of the things you'd want to put in your apps, but you might still have to build your own model. And then you have to learn about neural network architectures and things like hyperparameters and activation functions. My Keras tutorial explains some of this. And if you've looked at online courses on machine learning, you've probably seen a lot about efficient algorithms for gradient descent with complex math. As an iOS app developer, you don't need to learn any of that. Your job is to learn what high-level tools exist and how to use them effectively. When researchers develop a better algorithm, it finds its way into the models without you needing to do anything special. So here are all the Apple things. There's CoreML and its existing image models. There's CoreML tools to convert models created with other tools. There's Turi Create, which is Apple's first transfer learning tool, but it's in Python. And there's CreateML, which is transfer learning in Xcode and Swift. Apple frameworks include vision, natural language to process text, speech to convert speech to text, SiriKit to use Siri in your apps, and Gameplay Kit to evaluate decision trees. Vision is the most popular Apple framework. Yeah. It's easy to use in your apps to detect faces, including small faces or faces partially hidden by hats or glasses. And you can get face landmarks, the eyes, nose, and mouth, in case you want to draw hats and glasses on a face. And it can detect rectangles, text, and barcodes. If you have an image-based CoreML model, Apple recommends that you wrap it in a vision model. So I'll quickly show you how to make requests to the Playnode vision framework. There are two types of request handler, image and sequence, and this code is for the image one. Each type involves three objects: request handler, a request, and a request completion handler. You need one request handler per input image. You need only one request per completion handler, and the request handler can perform an array of requests. Okay. The first thing Apple provided with CoreML were these 6 ready-to-use models. But these models were designed for back-end inference. When you're going to add a model to your iOS app, size matters. So these 3 are relatively small, 5 to 25 megabytes. These 2 are around 100 megabytes, and VGG16 is 554 megabytes. Size is proportional to the number of parameters the model uses, which is related to how accurate it is. ResNet 50 has 25.6 million parameters, and VGG16, 138 million. I'll say more about size when we get to CreateML. Just remember the range of sizes here is 5 to 550 megabytes. If you can find a model that was created by one of the green tools, you can convert it with CoreML tools. And the purple tools have their own CoreML converters. Create ML and Turi Create make it easy for you to create customized models for the most common tasks. I'll show you them a bit later. I'll talk about image classification, but a lot of this also applies to the other tasks. You need a customized model when something like ResNet is too general and doesn't classify into the classes that you care about, like healthy versus unhealthy snacks. None of the general models is going to have these two classes, but they have learned a lot of features that help to classify images. So you transfer their learning about features to your data and classes. The general model is called the base model for transfer learning. The CreateML image classifier's base model is Vision Feature Print Screen, the catchy name for the Vision Framework model. Transfer learning processes each image through all the layers of the base model except the last, the classifier. The other layers extract features, like the ones in Eileen's talk, that are useful for classifying images. Instead of the base model's final classifier layer, transfer learning trains a custom classifier to get the classes that you want. To use transfer learning tools, you just add data. But actually collecting and cleaning data is the most time-consuming and expensive part of machine learning. These are some of the 4,800 images for a healthy snacks classifier. And some of the images have people in them, because we expect the app will be used in situations with people. The dominant part of this image, the blue shirt, has nothing to do with the food. But if you have too many training images like this one, it could teach the model to associate large blobs of color with certain foods. Ideally, you want a lot of images, but often that's not possible. Data augmentation generates additional images from your data set by cropping, rotating, blurring, changing the exposure, and so on. So how do you actually do this? I'll start with CreateML because that's where Apple expects you to start. CreateML's image classifier is a spectacular party trick, drag and drop training. It's a macOS Swift playground, and 2 lines of Swift code create and show an interactive window in live view. It's all very familiar. The training dataset contains subfolders, each named for a class, like apple, banana, orange. The image classifier automatically uses the subfolder names as the class labels for the images. When you drop in the data, it starts extracting features. For our 4,800 images, it took 35 minutes on my old MacBook and less than 3 minutes on my new 6-core i7 with Radeon 560 GPU. Purchased in July. The last step, training the classifier, takes only a few seconds. After training, it shows training and validation accuracy. What's validation? Well, before training, it sets aside 5% of the training images for validation. And after each iteration, it classifies the validation images and computes the error. But this error does not feed back into the training. At the end of the training session, if the training accuracy is a lot higher than the validation accuracy, it's a sign that the model has learned odd things about the training data that do not generalize to the validation data. This is called overfitting. In this case, 91% training and 89% validation is okay. Selection of the validation set is random, so validation results can change every time you train. After training, that arrow that's showing there, the window prompts you to drag in some test data, which leads to the question, what's the difference between validation data and test data? The model classifies validation data while it's being trained, but you should run the test data through your model only after training is completely finished and you like the model. You're happy with the model and then you test it. Don't tweak your model to improve the test performance. This would influence the training and then you won't really know how well the model will handle new images. You mainly use validation accuracy to see whether your model is overfitting. Here in the blue box, after 5 to 15 iterations, training and validation accuracies are pretty close, about 90%. But in the red box, after 25 to 40 iterations, the training accuracy is racing off to 100%, while the validation accuracy is actually falling to 85%. If you didn't have this validation info, you would think your model was perfect, but then it wouldn't perform well on new images. In this case, you probably should have stopped at 15 iterations. If you don't like the training results, don't use your test data. Just restart the window and click the disclosure button to show 3 options. You can increase the max iterations for training the classifier. So if your training and validation accuracies are close but not very high, you can do more iterations to improve the model. But if it's overfitting, more iterations will just make it worse. You can supply your own validation data set, so it's always the same. And then you can compare results when you're making other changes. And you can augment your data. This is the only way CreateML helps you to overcome overfitting by adding more data. The window lists the 6 augmentation options from the most effective crop to the least effective flip. If you check more than one option, the classifier applies them in that order. Selecting crop creates 4 new images, so feature extraction takes almost 5 times longer. Checking all 6 options creates 100 augmented images for each original. That's actually only 100 because the number of augmentation images is capped at 100. When you're happy with the training and testing, you can save the model as core ML. You drag it into the project navigator and it generates a class. Do you remember the sizes of the ready-to-use models? It was 5 to 554 megabytes. A transfer learning model usually includes most of the base model, the layers that extract the features. So if the base model is ResNet, the custom model is still around 100 megabytes. The size of this model is 312 kilobytes. Because the Vision Framework model is included in iOS 12, so it does not go into your custom model. That's supposed to be a clap. Okay, once you have your model, so this is called Healthy Snacks, you can create one in the code and you wrap it in a vision model to take care of converting input images to the right format. And then you request a VN Core ML, you create a VN Core ML request with the model and the completion handler. It's a lazy var because you need only 1 request per completion handler. And then you create a VN image request handler for each image and tell it to perform your requests. The CreateML text classifier doesn't have a GUI. The example in the documentation shows input coming from JSON or CSV files, but the CreateML video demo shows an interesting feature that is not in Turi Create. You can put the text data into subfolders just like the image data sets, and labeled directories will create labels from the folder names. Oh, and Matt Thompson wrote a really great tutorial using the text classifier. So, Turi Create. It's Python, but you get 5 more task-focused toolkits in addition to image and text classification. So you get recommender, activity classifier, object detection, and this cool thing called style transfer, and also image similarity. Apple might add them to CreateML sometime, but if you want to try them out sooner, the other half of my CreateML tutorial tries to make it easier for you to get started with Turi Create. You install Anaconda and use its Navigator GUI to import the turienv.yaml file that comes with the tutorial. And this sets you up with Turi Create, and you can launch Jupyter Notebook from the GUI. A Jupyter Notebook is like a playground that runs in your browser. And the tutorial shows you how to create an image similarity model for the cats and dogs dataset. Turi Create is a little more manual, but not much more than the CreateML text classifier. To get class labels from the subfolder names, you do have to do some path wrangling. And then you can train with the same base model as CreateML. If you're using my YAML file, you'll have to update Turi Create to the current version 5. Being less automated and more hands-on, Turi Create gives you more control over visualizing results, like this heat map of the confusion matrix for the test data. The horizontal axis is the predicted label, and the vertical axis is the true label, so you want numbers on the diagonal to be high with warm colors. Any non-zero numbers off the diagonal are images that the model got wrong, so you would try to get better training images to help the model distinguish cookies from muffins, for example. So try it. Start with machine learning in Xcode and Swift, with frameworks and CreateML and CoreML. If you need one of Turi Create's toolkits, try Anaconda and MyTuriEnv, and maybe even venture into Keras. Where to go from here? The obvious websites and my Twitter handle. Oh, and just one more thing. Ray Wenderlich will be publishing a machine learning book for iOS developers. Pre-orders open soon, maybe as soon as next week. Thanks for listening, and please drop by my office hours if you have questions.